In many early mathematical traditions, numbers functioned primarily as tools for counting. They were used to measure land, calculate trade balances, track agricultural production, and regulate taxation. Surviving records from Mesopotamia and Egypt show highly developed numerical procedures applied to practical problems. These traditions demonstrate considerable sophistication, yet they treat number largely as a quantity attached to objects. This is before logic, a history of rules before they were written. In the Eastern Mediterranean during the 6th century BCE, a different interpretation gradually appeared within Greek intellectual communities associated with the figure of Pythagoras and later writers linked to the Pythagorean tradition. In these circles, numbers were not understood merely as quantities applied to things. Instead, number was treated as a structural property of reality itself. Surviving sources describing early Pythagorean thought are fragmentary and often written centuries after the period in which the earliest communities existed. Accounts appear in later philosophical works by authors including Aristotle, Iamblichus, and Porphyry. These sources differ in detail and occasionally reflect the philosophical concerns of the authors themselves. For this reason, reconstructing the precise doctrines of the earliest Pythagorean groups remains difficult. Nevertheless, a consistent theme appears across many accounts: the claim that number constitutes the underlying structure of the world. In this interpretation, number was not limited to counting. It described relationships, proportions, and arrangements that were thought to organize both physical and abstract phenomena. Instead of attaching numbers to things after the fact, the Pythagorean framework treated numerical relationships as the patterns from which things arise. One of the clearest expressions of this approach appears in the study of musical harmony. Greek musical theory examined the relationships between string lengths and the sounds produced by those strings. Certain ratios between string lengths corresponded to intervals perceived as harmonious. The relationship between a string and another half, its length, produced a particular musical interval. Other ratios generated additional intervals that listeners identified as stable combinations of tones. Within Pythagorean traditions, these observations were not treated merely as acoustic phenomena. They were interpreted as evidence that harmonious relationships arise from numerical ratios. The structure of sound could therefore be described mathematically. The important development was not simply the recognition of numerical ratios, which could be measured empirically, but the broader interpretation that numerical proportion represented a fundamental organizing principle. This interpretation extended beyond music. Pythagorean writers and later commentators attributed numerical structure to geometry, astronomy, and cosmology. Geometric figures were understood as expressions of numerical relationships. Astronomical motions were interpreted through proportional models. The arrangement of the cosmos was sometimes described using numerical harmony. The central shift introduced by this tradition was therefore ontological rather than procedural. Earlier cultures had already demonstrated sophisticated numerical techniques. The Pythagorean contribution lies in the claim that number describes the structure of reality itself. Number was treated as something closer to form than quantity. This perspective required a different way of thinking about mathematical entities. Numbers were not simply labels attached to counted objects. They were treated as abstract structures capable of existing independently of the particular objects they describe. In later philosophical language, numbers were increasingly associated with forms or principles that organize phenomena rather than with measurements alone. The idea that reality might possess a numerical structure also encouraged the study of mathematical relationships for their own sake. Once numbers were understood as structural rather than purely practical, the investigation of their properties became an attempt to understand the organization of the world. This contributed to the gradual emergence of theoretical mathematics within Greek intellectual traditions. At the same time, the surviving evidence suggests that early Pythagorean communities did not sharply separate mathematics, philosophy, and religious practice. Ancient sources describe ritual practices, rules governing community life, and symbolic interpretations of numbers. Some numerical relationships were treated with special significance within the group. Because these descriptions come from later authors, scholars disagree about how literally they should be interpreted. Some historians treat many of the reported symbolic practices as later embellishments or philosophical reinterpretations. Others suggest that numerical symbolism may have played a genuine role within early communities. The available sources do not allow the internal doctrines of the earliest Pythagorean circles to be reconstructed with certainty. Despite these uncertainties, the conceptual shift associated with Pythagorean thought proved influential in later Greek philosophy. Plato, writing in the 4th century BCE, treated mathematical structures as closely related to the organization of reality. Later, mathematical traditions also adopted the idea that abstract relationships could exist independently of the physical objects that display them. The transition from quantity to structure therefore marked a significant development in the history of reasoning. When numbers began to be treated as patterns governing relationships, mathematics acquired a role beyond calculation. It became a framework for describing order itself. This change did not immediately produce formal logical systems. Greek mathematics would continue to develop gradually through the work of multiple traditions over several centuries. Nevertheless, the interpretation of number as structural introduced a way of thinking in which abstract relationships could be treated as stable objects of investigation. The idea that patterns could be studied independently of the particular materials that display them later became central to geometry, algebra, and formal logic. In these disciplines, relationships between elements are analyzed according to defined rules that remain stable across different contexts. The historical record does not allow the precise intellectual pathway from early Pythagorean communities to later mathematical systems to be traced in detail. The available evidence suggests a gradual process of reinterpretation, transmission, and reconstruction across multiple philosophical schools. What can be established with greater confidence is that the Pythagorean tradition introduced a way of describing the world in which order could be expressed through numerical relationships, rather than through narrative explanation or mythic genealogy. Numerical proportion provided a language for describing stability and structure. Within the broader history of reasoning, this development represents an early step toward treating abstract relationships as objects that can be studied independently of their material instantiations. Later systems of geometry, logic, and computation rely on this assumption in different ways. In the next episode, we will examine stability and flux, Heraclitus and Parmenides,